Before going there to the actual topic, these are just the glimpse of Altair. I'm sure many of you already know these things, and I'm sure many of you are attending our series of webinars, and you may have seen this slide. But for the people who have not seen, or who know little less about Altair, for them this is for them. So in short, what the numbers, it's little old. 400 million is what is the revenue on 2018, and we have as many as 100 plus software products and 8,000 customers, thanks to all of you. And among these 8,000, there are 60,000 users who uses our solutions, which includes all the Altair solutions. So now just to give you a glimpse of what are covered under Altair solution, as you have seen, there are more than 100 products. So all cannot be shown in this slide, but this has a bucketized view of all those softwares, and out of which the red one, which we are going to talk, in which SimSolid belongs. So that is called simulation driven design, and I take care mechanical sides, mechanical in the sense that mechanical side, you can say, of the simulation driven design. Now coming to SimSolid, why we need SimSolid? Okay, so the whole purpose of introducing SimSolid is to rapid simulation, and in other words, which will ensure rapid development. And why you need rapid development? This is not any secret that shorter the development cycle, the sales will be higher. So that's the whole idea. And through SimSolid, we will achieve that, and that's the reason we introduce SimSolid. And it's not any secret that we need a shorter development, and many companies are everybody is trying to achieve that. If you remember our typical automotive product development cycle, which used to be say around 10 years back, which used to be say 50 months or so in a new product development. Now thanks to all these FEA tools and all, it's now around 36ish or something like that. Companies want to reduce it further, and that's where products like SimSolid will help them drastically. Why we introduce SimSolid? There are certain pain areas what we identified with the conventional way how the product development happens, especially the simulation part of it. So speed is one of the major pain. Complexity, okay, and loop between your design and CAE. So these three things are major bottleneck what we found out while designing or developing SimSolid, and this has been taken care of on SimSolid. You will come to know when we'll go in detail of the demonstration. Now, what are the benefit you are getting with using SimSolid? SimSolid, if you see this slide, it will take some time to explain. Let me take. So if you see this portion, this is the bottom pie, which is talking about the SimSolid led enabled development, and the front one is the traditional approach of doing your development in terms of simulation and design. Okay, so now if you see the top one, which has many sections, okay, most of those time consuming sections are this one, which is blue, which is called solution, and then there is the orange one, which is called meshing, and then there is a gray one, which is actually connections creations. Okay, so these three major chunks, major pies are taking major chunks of time if you go conventionally, which are either altogether eliminated or reduced drastically within SimSolid, and that's why you are getting altogether time saving in the range of say 80%. Benefit number two is that because of the way SimSolid works, which you will come to know maybe very soon through the demonstration, what I am going to show is that it now possible to practically do simulation on any geometries. You don't have to shy about the size of the geometries, which were the case if you see the classic approach, because up to certain after certain level of geometry, geometric complexity as well as largeness of geometric assembly size. This goes exponentially over simulation time and effort. And because of this two benefit, we get one benefit which is the kind of derived benefit of these two, that is called design space exploration during the product development. What is this? I'm sure you know this term, design space exploration, in the sense that you explore as many options or concepts as possible through some algorithmic means by some simulation. Okay, so that was not easy till date, because of the reason that each of the simulation, if you want to go through each concept through simulation, it used to take huge amount of time. And so many a times what we have to do in past is that we have to take decision based on our experience or maybe the available resource. So say that you have 10 designers, one CA guy is doing some priority project, maybe you just give one concept and that's it. So that don't have to do here, because the whole idea of doing simulation within SimSolid itself is so less time consuming and so simple and so powerful that you can now have a luxury to go through all those concepts whatever you want and then choose the best one, rather than going for those gut feeling or experience or priority based way. So what is SimSolid? We are talking about SimSolid. So we are telling the qualities of SimSolid and what it can do. So, but what is SimSolid? It is a new paradigm for simulation, and that is very important. It's actually a new paradigm, and it's a structural simulation software that operates directly on original unsimplified CAD geometry and does not create mesh. So all these bold letters, bold words are literally true within SimSolid. So it's a structural simulation tool. It operates on original unsimplified CAD geometry, means you don't have to simplify the geometry for a simulation, and it does not create mesh. And most important is it gives result in seconds to minutes. So that's the power of SimSolid, and that's why it is spreading within the industry like rapid fire within the industry. Now, without further word, I will just like to show you the tool itself, so you will probably appreciate. So the idea over here is today's is that I have not made a presentation, but let me show my plan, what I'm going to show today as far as demonstration is concerned. So I will have 4 or 5, or rather 4 demonstration. The first one is your design space exploration example, what I was talking. I was a designer, so I'm fascinated about that capability of SimSolid, and I think there's a real powerful feature of SimSolid. Everybody should use it. So that's why I'm going to start with that. Then I'll spend some time. It's not a demo. It's kind of a workflow, showing workflow on connection, because connection is very important and powerful feature of SimSolid, connection and weld, how it is created and all. Then I'll go to the next demonstration, which is on nonlinear contact analysis, and then I'll go for one demonstration of frequency response, and then followed by a thermal analysis. And if time permits, we can probably. Oh, I'm sorry, I have not added a modal analysis, so I will show a modal analysis as well. Okay, so we have a lot of things to cover. Let's hurry up. Okay. So this is the tool. If you see that this is a humble looking GUI, it don't have much of these icons really activated, and that's for purpose. So we don't want to confuse you with so many icons which are not necessary. Okay, so all you need is these 2 icons now. So what I'm doing is I am now importing a geometry of this. Oh, so before showing the geometry, I should have shown that what all the file formats it can support. So in short, SimSolid can support all those popular file formats, which can be your neutral file format. That means those Parasolid, IGS, then Step, Jetty, and all. And also it supports whole bunch of proprietary file formats such as your CATIA, ProE, Unigraphics, SolidWorks, and so on and so forth. Now, as soon as you will import a geometry, so this is the geometry what I imported. it will pop up with a connection creation, automatic connection creation window. So now, since this is a web-based training, so I'll go a little bit of deep on detail on each of those icons and all as much as possible. Although I'll restrict myself not to go too deep so that we can save some time. So what the guys does over here is that it kind of help you to create connection automatically as soon as you import a geometry, but that is not compulsory. Okay, you can safely cancel this and you decide to do something else as well. That is possible, and especially if you have other idea of creating connections than automatic connection, so you can also do through welding and all. So that for that purpose you may not have to go for automatic connection. And at any point of time in later stage, if you want to bring that automatic connections, then you can always bring that icon over here. Now, before going further, I'll do two things. One is for beautification of this assembly, that is auto color, so that I mean, of course, it's a beautification, as also you will see that number of parts and their boundaries and all. And then second, I would also want to give you an idea that how big is this assembly, so that you can appreciate the time it should take, and vis-a-vis the time it will take to solve. So right now it is a 1.2 meters, roughly 1.2 meter is the size of the assembly. What you can say, there's a quite a big assembly. It's not a very small assembly. And if you go over here, you can understand your number of components. So if you see that there are around 85 components, again, it's not a very small. At the same time, in SimSolid's language, it may be not very big as well, because we handle as big as say 8,000 component train assembly. I mean, there is a train compartment, complete train compartment has been simulated very recently with a company called ICF. Okay, so now going ahead, so what we'll do, so first thing is, of course, you have to create connections. But now right now I am not doing a welding connections. I'll show you a separate session on that. I mean, separate file on that. Right now what I'll do is I'll actually take help of this automatic connections only. And here you have two things. One is gap tolerance and penetration tolerance. What it is doing is basically, as I said, that SimSolid don't require a assembly to be recreated for analysis. It can take existing assembly, even if the assembly is not a perfect one. For example, your assemblies made constraints are not perfect, those are not 0 0, so then you have a gap. So that gap's value itself you can give, and then still it will be able to connect. And same is that true if your assembly is parts are interfering with each other, so that is also possible. So SimSolid don't the design of SimSolid is such a robust that it believes that real world is non-ideal, so it still can operate. Okay, so let me create connections. Okay, so it has created connections with a fraction of time. So if you see that this many connections it has created with between all the possible nearby parts. Okay, so now by default these connections are bonded connections, but you can always override and create another types of connections as well. But for this particular purpose, this bonded connection is good enough. Okay, second, what you have to do is you have to create a create what is called material. Okay, select material rather. Okay, or create material, both the way it is possible. So there is a material library which is, I would say, rich in the sense that it kind of covers pretty much length and breadth of the engineering material what is used in the industry, which includes linear material as well as non-linear material. Okay, so material non-linearity has been taken care within the material database if you want to use it, or you can create your own material as well. For now I am not going to that, but it's possible to do that. And then let's take the steel as my material and apply to all the parts. Again, you have a choice whether you want to apply a single material to all the parts or you want to go for individual materials. So all those options are possible. Next, as soon as your material definition is done, what you can do is you can choose your type of problem what you are going to solve. So again, this is quite rich, although this is very simplistic GUI and it looks very simple, but it is quite powerful in terms of the physics what it can solve. So for example, it can solve linear structural, non-linear structural, which includes your contacts, geometries, and your contacts, geometries, and material. Okay, you can solve modal and those frequency related problem, and you can also solve dynamic problem, which include FRF, random response, transient, and you can also solve your thermal problems. Okay, and you can couple this thermal with structural as well. So in short, as far as the structural requirement of an engineer is concerned, this is pretty much covered across in SimSolid. So right now what we'll do is I'll go and choose the structural linear problem. Okay, so as soon as I do that, what it will do is it will repopulate this left hand side bar, ribbon bar, what we call, which is dynamic. And each of the type of problem you choose, these icons will change to make you less confused. Not only that, you can even, if you choose the section of your model browser, accordingly these things will also change. So make sure that it will also allow to appear the icons which are really possible to work on that section. Okay, so now what I'll do is I'll apply some support. So this is the support I am applying. So let me apply support, and then I will also apply what is called my force. Okay, so let me apply some force here. So in this surface, I'll apply force in negative x direction, maybe say around 1000 Newton. And then I will also apply a force in the positive x direction in this plate of, say, again 1000 Newton. Okay, so these are two forces I have applied. Now once you have that, you have defined material, you have created connections, and you have applied force, and you have applied support. So that's it. SimSolid don't need anything compulsorily. I can see some of the hands you raised. Please write those comments in your comment section, question section, so that we can answer this if we am not able to answer it now. And if you are facing problem regarding my internet speed, then that also you let me know. So one of the organizer can let me know that, then I can moderate my speed accordingly. So now let's fire the run. Okay, so that's the fun part. Okay, so let's fire the run. So I am solving it live. So this is where I am started running this simulation. Okay, and it will do all those calculation in different stages, and then it will show you the result. And don't blink your eyes, because this is blazingly fast. You may actually miss the climax. Okay, so if you see this over here, it run is complete, so it result has appeared. And as far as the time goes, it took around 14 seconds for a assembly of 85 components, which is 1.2 meter of size. So that's kind of amazing. Okay, let's see some of the results. So these are the results. So almost all the types of results are covered. So this is the displacement. I can animate it and to understand what is happening, whether it is meeting the physics or not, or whatever. So those things I can do. I can also do something like this. So let me, there is a unique way of saving this result in a particular orientation. Okay, so that is called bookmarks in SimSolid's term. Okay, so there is called displacement. So let me make it displacement. I can also go and check the stress. So among this stress, maybe I would be interested in this particular zoom position. So let me again save this. So let me make it stress, and so on and so forth. Okay, I can also go with many other types of results. So these are there. So there are principal stress, then strain, then safety factors. So then energy density, then you can have a component of stress, strain, displacement. So all types of possible results you might be interested as an engineer, or you may be, would like to take a probe and go for certain points. Okay, so that is also possible. You can even do something like this. You can even go for, you can give an evaluative average. So then in that case, it will take all the points, and then you can average it out. You can also go check other type of result. For example, you can understand what is called your reaction force. Okay, so that is very important understanding. Sometimes engineers do need. So mostly it is by default, it is on support, but you can also understand the different connections as well if you require. and from the support you can draw many useful calculation, I mean useful conclusion that you already know. Okay, but this is a tool what you do, what you have to look. And at any point of time you can export this result as a CSV, so that is also possible. You can also understand the very important parameter which is called bolt and nut forces experienced by bolts. Okay, so in that you can understand that axial force, shear force, bending moment, and all those in of each of those bolt. Okay, and from there you can have a important conclusion about your bolt loosening and all those things, or maybe whether bolts are sufficiently sized, or it is oversized, or over pitched or under pitched. So all those important conclusion you can make out of this table. So having said that, let me go back to the stress plot. Okay, so now in this stress plot we have this stress, and from this stress plot at one glance you can understand there are areas which are not so stressed. Okay, so as an engineer, what I could be interested in is that I would like to redesign this part by removing some of the material in some of the areas where it is less stressed, and I want to understand that what will happen if I bring those geometry. So that is what I meant by design space exploration. I can bring a geometry which is actually exactly where it is, some of the areas where it has cut out, I cut out. So let me bring that geometry. So I will bring this. So then what will happen is that's where the is that uh, if you see that it is trying to create another design study. Okay, so that is what is design study 1, and then this design study 2 is been created. And if you see this design study, this is different than what is design study 1. So this was my design study 1 geometry, and very easily I could import a geometry which is my design study 2, where I have this cutouts made to make sure to check whether my new concept is strong enough to and lightweight, so that I can take this concept rather than the complete other concept, which is there is no cutout. So to understand that structural performance of that design study 2, all I have to do is I don't have to recreate these things or the steps what I followed creating the design study 1. All I have to do is I just have to hit the analyze button. Okay, and rest of the things has been automatically created for me. This looks very simple for a one concept, but if you are dealing with say 10 concepts, okay, each time creating connections, assigning material, then applying right force in right location, applying constraints each time. There are two difficulties. One is of course it is cumbersome, and second is there is a chance of human error. Okay, that things you can avoid. Now if I go back to my displacement study which I saved earlier, this is the design study 1. Okay, so this is the displacement. If I click over here, it will automatically switch and show you the same quantity of your result, but for the design study 2. Same is true for your stress. So if you see that this is my design study 1 stress, and if I go over here and click, you will see in a same location, same orientation, how the stress are varying. Okay, so this is the most important thing, what to my opinion, as far as the design space exploration is concerned, and I would request all of you to use these features. Okay, having said that, you can also do some more things. For example, you don't have a geometry as such as far as design space exploration, but you have some idea to do another, maybe doing another type of analysis. So all I have to do is let me copy these things. I can copy each of those things. I can copy design study, I can copy a load case. So I have copied this load case. Now what I want to do is let me delete these things. I want to do a bolted joint analysis. Okay, so I want to torque a bolt, and I want to understand what is happening to this torque bolt. Okay, so what I'll do is I'll go over here and find a bolt or nut. I can torque both. So, but let me torque a bolt where there is no nut, because there is a nut, then it's essentially have to torque a nut. So, but I want to torque a bolt. So let's go and find this bolt. And then you have to define a few of the inputs. For example, one is thread pitch. So maybe I'll go for 1.25 thread pitch. So 0.001 to 5. So that's my thread pitch. And then there are a number of ways you can define your torquing. One is you can define the number of turn you are giving, or you can give the torque directly and specifying its friction coefficient, or you can give a axial force which is generating out of the torque. So for the time being, what I'll do is I'll just apply the number of turn, that is basically the turn after you after you finished your tightening your bolt, in the sense that this is after the bolt head, flat surface of bolt head reach to the mating surface. So this is the extra one turn you are giving. Okay, so now once you have that, all you can do is you can again analyze this. So let me analyze this, and then we'll understand the result. So let's now see what is happening. So if you see this, let me make it true scale so that it will show more realistic. Now if I animate this, so if you see this over here, so this is what is your stress. So let me again show it in true scale so that you will understand how much it is really going. And if you see, this is very important thing, because you will as an engineer would understand that how it is really getting torque, and you can also understand that how the stress or the force is getting transferred from the tightening the bolt to the part and mating parts and so on. So this is a very useful example. You can also go and recheck your bolt table. So if you see this over here, so there are, I don't know which bolt it is, so let me understand this bolts info. So this is basically your bolt ID is name is grapple 64. So if I go and find this grapple 64 over here, so this is the bolt. Okay, so this is the bolt we are talking about. Now if you see that with respect to the rest of the bolt, this has higher amount of axial force which is withstanding by this bolt, and other forces as well, which is obvious and which kind of correlate with the physics what we are talking about, and which in turns correlate with the accuracy of SimSolid. So this is what I wanted to show. You can also do a very quick study of as far as the factor of safety is concerned. Sometimes that is quite useful. So if I go to my design study one, so let me go to my design study one, and let's go to the result, and then let me go to the safety factor. Okay, so now if you see that it has very high safety factor, so in the sense that it can very easily show that which are the area which is going beyond your target safety factor, which is in this case is 3. Okay, so if anything goes below 3, so that will fall into red. So but right now most of the things are higher, so that's why you will see everything is green. So that means it is anything, all the safety factors are more than 3. So now let me change this acceptance criteria itself so that I can see some red areas. Okay, so let me improve this, and let me improve this, let me increase this low factor as well, low factor slider as well. So let me go over here and down, let me go till the time I get some of the factor of safety values. No, it is not coming. So maybe most of the safety factors are very high. So what I can do is I can go and change this areas. Okay, so maybe low factor is here. No, I'm trying to, let me see if I can edit this. Okay, so maybe I will make it. Okay, so I manually edited this because this is not a very practical solution. I mean, it's not very practical because the applied force is low, but this is just to demonstrate that what kind of contour you would expect if your some of the areas goes beyond your, beyond your target values. Okay, so that's what I wanted to show. So let me make it also as 76. Okay, so what it is showing is that the area which are less than 76 factor of safety, assuming that 76 is our target, so that will show in red, and the area where the factor of safeties are 76 and 80, it will show into yellow, and then beyond 80 it will show in blue. So just one more table, I thought it is sometimes useful for the engineers. Okay, so that's it I wanted to show as far as the first analysis is concerned. Now moving on to the next one, let me close this. or maybe I should have opened another study, but okay, I just closed it. So what I'll do is I'll spend some time into contact and connection definition. Okay, so let me open this. So how to handle the different types of welding connections, especially. So you already saw that how to handle the automatic connections or non connections where you don't actually create weld, but you actually create contacts. Okay, but here what I'm going to show is your how to create those welding connections, different ways of creating welding connections. Okay, connection line item in your project tree, and then you have to go to this any of those connection type, which includes your automatic connections as well, or maybe you can even do manual connections. But what I'm interested now is creating welds. Okay, so that welds itself can be of two types, or rather two types. Yeah, one is your spot weld, and then another is your fillet welds. Okay, to create spot welds, there are multiple ways possible. One is your you can select the spot, so location. So I can create those locations, pick those locations, and it will I can choose the spot diameter, and it will create the spot weld. So if you see that it has created the spot weld, make sure that you choose the location where at least another part is there, another plate is there, otherwise there is no meaning creating spot weld. So basically it is 2D weld what I am trying to create. Okay, another way of creating spot weld is to bring the CSV file where your CSV you have to do is you have to bring this up, not this one. So let me go over here, product training SimSolid web training connection. Okay, so this is my table CSV file, and if you see that all those points has been automatically picked up, and it has if I say okay, it will create those spot welds. So if you see that it has created all those spot welds over here, so you have see so many spot welds are there. So let me delete all. Now that is spot weld. Now how to create fillet welds? Again, very simple. There are multiple ways possible. So let me expand these things. Okay, so there are 1, 2, 3, and 4 ways you can create actually fillet welds. Okay, what are they? One is called so for any of this weld, there are these options which are common. The first one is your size of the welds, and then there is minimum length. Okay, so what it does is basically size, as you know, it is this size of this weld, and minimum length is where what it does is it try to if any length falls below this minimum length, any edge which falls below this minimum length, it simply don't weld that area. So assuming that that beyond minimum length, your welding torch will not move. Okay, so that's what it specifies. Now after that, you can also define your intermittency, in the sense that if you don't want a weld to be continuous, then you can define intermittency by means of pitch and the weld segment length. Now after you define these two things, either define or don't define, but after you taken decision about these two things, you have to go for one among these 4 options to create weld. First option is your master weld. What is master weld? In that case, you choose a part which is supposed to be a master. So this is my master, and then you choose a part which is to be slave, in the sense that between master and slave it has to be created weld. So then as soon as you say find weld, it will create the welds within this specification of your whatever you have given as an input. Now it will find all the possible edges which are to be welded, but you can always delete this. So for example, I can go and say that delete this edge, then you can keep which are absolutely required. Okay, so then you can say okay, and it will create the welds. So if you see this will create the welds. Okay, so let me delete this again. There are another way, there are the other ways as well for creating weld is concerned. So for example, group weld. In that case, if you have multiple parts and you don't are not sure, or if you are, it will be tedious to select master and slave. Other than that, what you can choose here, you can choose the group of parts. So that how you'll do, you will just simply box select. Oh, sorry, you simply box select, and it will find all the parts and say find weld. So it will find all the possible permutation and combination of weld, and you can keep or delete whatever you don't need. Okay, so that is another way. And the third way is to creating weld by line or edge. Okay, so in that case, you are not selecting master and master slave. All you are choosing is the edge between which is shared by two or more parts, and then you say find weld, and then it will try to find out the welds, and you can create those welds. The last option is your weld from solid. So many are cases what happens is you model the weld. So for example, this weld has been modeled over here, and you want to use those modeled weld which you already modeled in CAD to be used as a weld rather than you defining on your own. So to do that, there are many ways. One among them is, of course, you can select this part one by one, or the best way is if you have hundreds and thousands of such parts, you give it a common starting name. So for example, if you go over here, all my such parts are starting with what is called fi. Okay, so fillet. So now if I search by word fi, so I'll get all my parts which I wanted to be a weld, solid welds, and say find weld. So then what will happen is it will find all the parts, all the solids whose name is starting with fi, and as soon as we will say find weld, it will find the surrounding geometries to create welds, and it will create all the welds. And again, if you want, you can delete any of the welds which you don't want. Okay, so that is another way of creating weld. So in short, we covered the spot weld and as well as fillet weld. And you can also create another connections. For example, there is automatic connections, which are essentially is the simplification of the weld. Okay, or where you want to define some other behavior, for example sliding behavior or separating behavior, that time you will not prefer weld, you will go for creating connections. Okay, so that connection can be automatic or that connection can be manual. Okay, that connection manual in the sense that, again, similar way like what you did for weld, you can choose part by part. So for example, this is my master part and this is my slave, and I want to create a connections, find connections, so it found a connections. Similar way, I can go to create group connect or maybe edge to surface connect, but those are the connections where you have a flexibility to define the stickiness of those connection behavior. You can make it fully stick in the sense that bonded, or you can make it sliding where it will not leave the surface but it will slide, or you can make it separating, which is a kind of falls under nonlinear connection, which you will see in a later part of the demonstration. But to with this today's time frame, I think this much is sufficient as far as the connection and welding is concerned. So I'm ending this connection and welding demonstration over here, and I'm moving to the next topic. If you have any question, of course, you drop those questions in the question answer. We'll try to answer as much as possible. Now, moving ahead, what I'm going to do is I want to do a what is called modal analysis. Okay, so to do that, let me find out the model which I have not saved. So let me see if I get those things over here. I don't know which chapter it is. Let me just give me a couple of seconds. So this modal analysis is in which chapter, which problem? Let me see this. No, I'll not take the single part. Okay, so I want this. So this is 3B. So I think I have this one. So let me bring that model. So product training SimSolid student exercise chapter 3. So this is one. So I want to do a modal analysis just to show that how modal analysis and or how easy a modal analysis to be how easy it is to carry out a modal analysis within SimSolid. So the first step, of course, bring your geometry or maybe saved assembly of SimSolid. So right now I have brought. Now, second thing is, of course, you have to, since it is assembly, you have to make sure that you create connections like the way either you create welding or adhesive or maybe something else. I am going ahead with automatic connections and say okay. All you have to make sure that all are connected. And after that, what we will do is you will go for choosing your simulation type as modal. So I am going ahead with this and say I want 9 modes to be extracted, and then I'll apply the constraint. So this is the surface what I have to constrain. So this is my constraint area, and that's it. I can go for doing a modal analysis with as many number of modes as I want. And also modal analysis is very important for many reason, as you know, that one among them is of course to identify the frequencies or modes of the parts. There are many other derived application of modal analysis as well. For example, your checking is your uh, connections of a large assembly. So whether your assembly is properly connected or not, or maybe your assembly has assembly is properly constrained or not. So all those things you can very easily check with modal analysis. So now how to do modal analysis? Again, very simple. You go for solve. So now this is another feature of SimSolid. So in case you don't define any material, you have the option to choose a material as a default material. Okay. So in that case, you can simply say that I want to use this default material if you don't define any other material. Okay, so now it will run those modal analysis, and it will show you the results are ready. Again, super fast it is. So now if you go, you can understand all those modes. So this is my first mode, obviously. This is my second mode, again very obvious because this is the weakest link. Third mode, fourth mode, fifth mode, and so on. So after that, maybe some modes are coming in that towards the base side as well. So these are the modes. Okay, so now this is very important because you are understanding the modes, modal frequency, as well as the modes. You can also understand many other things. So for example, if I go over here, I choose a particular mode, so the first mode. So what is my first mode? So first mode is moving towards, say, not exactly towards Z, but somehow closer towards the Z axis. Now if I go over here and pick this icon, so this is what is called parts ranked by amplitude. So what happens is, in case you have a very large assembly and you are actually doing a modal analysis, now if you want to understand the, just a minute, I think it is not important call. Okay, so if you want to understand that which among this part of this assembly has the is the weakest one, or which has the highest amount of amplitude. Okay, so then you can very easily understand those parts. Okay, and then probably as a result you can probably strengthen and all those things. So for this particular modes, this part is weakest, so that is obvious, right? Because this is there is only one side, it is fixed, and then it is moving in this direction. So this is a quite important tool in SimSolid, to my opinion, as far as the designers are concerned, because it will give you a very high level view of the weakest link in your assembly. Okay, if your exciting frequency is also in this direction, you would probably be interested in this strengthening these joints and all. Okay, so that is one part I wanted to show. The second part, what you can see is that what is called the participation factors. This is again very important concept. I'm sure you all know that. So what it tells is that in any particular axis, okay, so in any particular axis, which frequency or which mode is the most critical one. So if you see this one in Z axis, the first mode is obviously most important one. Why it is so? If you see the mode shape, you will probably correlate that better. So if you see that mode shape, it is not exactly in the Z, but definitely among this X, Y, and Z, highest contributors will be the Z. Okay, highest contributing direction would be the Z. Okay, so likewise, this for this simple case, it is easy to understand through the mode shape, but sometimes it becomes difficult. So that time you can probably take help of this table of your interest, and you can click and click so that it will arrange ascending and descending, and you can have the modes which will show the highest. So that's where it is the highest. And these please remember, these numbers are just the factor. This has no unit. It's not percentage. It's not have any unit. So this is the factor. So highest is the highest. That's it. Similarly, you can understand the X. So if you see this X, you will see that it's not the first mode which is important, but it is actually the third mode. Okay, you can also plot a histogram. Okay, so it'll also plot the histogram. If you see that in this particular X-axis, this is the third mode, which is giving you the most amount of oh sorry, fourth mode. So third mode is the lowest, so fourth mode is the highest. So make sure that this is the highest value. Okay, so if you see that from the histogram, it is pretty clear that the fourth mode is the highest contributing mode. Okay, so that is another important application of or rather conclusion what you can made out of this modal analysis. There are many other applications, namely this dynamic analysis, but for that we'll come back to the other example. For now, I'm stopping this modal analysis over here and move on to the next topic, which is I don't know what, which is actually nonlinear contact. Okay, so let me open that model. So let me close this. Let me open the model. Okay, so nonlinear analysis. Okay, so I'll bring this assembly. A simple assembly, but this is quite interesting to my opinion. Okay, so what I'll do is I'll first delete all these things what we have already done so that I can show afresh. So let me delete this as well. So these connections are created. Let me make sure that these connections are there. So all are bonded connections. So this part has been there, and likewise with automatic connections, these connections has been created, and that's it. Okay. So now once that connections has been created, let me make it a little more beautiful. Now what I'll do is I'll apply the loads. Okay, so sorry, I'll create the solutions. So first one, what I'll do is I'll create a structural linear solutions, and for that I'll constrain these areas. I'll constrain this four faces. Okay, and then I'll constrain this two and this two, so there is total four. So these four faces I'm going to constrain. Oops, kya ho gaya? So let me constrain. Okay, so let me make it, and sometimes, okay, so my four faces are constrained. So 1 2 3 4, make sure those are constrained. And then what I'll apply is I'll apply some loads over here. So I'll apply this load. It's just like a hanging load towards downward. So I'll go for applying force and choose this both the faces. So face 1, face 2, and I'll apply load in negative z direction. I would apply maybe around, say, 5,000 10,000 Newton. I hope that should be sufficient, because without that it will not be fun. Okay, so I have to make sure it is on negative z, so I made it positive z. So this is my negative z, and then I have applied this load. Okay, so that's it. And then my default is still I'll go for running this analysis. Okay, so let me go and run this simulation, and there are bolts and all those things. Okay, so now my result is done. Let me see the displacement. Okay, so let me see the displacement. So this is coming like this. Okay, let me stop the animation. Maybe I'll put it like this. And what I'll do is I'll take a snapshot, or maybe I'll stop this. I'll take a snapshot like this, and let me align it towards, say, front. Oops, front is not the one, so maybe I have to align it towards top, or maybe bottom. Yeah, so this is coming, but I want like this. Okay, let me take this kind of analysis. This is a snapshot, and then let me make it like this and take a snapshot. So this is my displacement snapshot. Displacement. And then I would also like to take a snapshot of stress, but what I'll do is I'll hide this part. I'll hide this part. I am interested more on this area. Okay, so let me take a snapshot like this and make it, name it as stress. Okay, stress. So my stress and displacements are there. Okay, so now what I'll do is I'll now introduce the, let me bring all the parts, show all the parts. Now what I'll do is I'll introduce the nonlinearity. Okay, so what I'll do is I'll go and make another load case, create, or maybe what I'll do is I'll create over here, and I'll make structural nonlinear analysis. And with that nonlinear analysis, I'll choose the separating contact as my contact type. So my load case 2 has been created, and here again what I'll do is I'll do the same thing pretty much. So I'll constrain this four faces, and this one, all these four faces are constrained. I'll apply load, same load I'll apply. These are the faces where I apply load, this one, and then I think I applied earlier 10,000. So 10,000, just make sure it is correct. Okay, so 10,000, that's the force I applied. And but only difference is that pretty much same. Only difference is that I'll go to this part and change the uh, contacts of this part to non-linear, in the sense this is now it is bonded. I will make it as separating. Okay, so but for that I have to find out which contact I am interested. So this is definitely one. These washers and nut and bolt I'm not going to change. So what I want is this one and this one. So these two contacts, what I'll do is I'll go and edit contact condition, and in structural 2 load case I want it to be separating. Okay, separating is good enough with the friction coefficient as 0.1. Okay, so that's all I have done. Okay, so what I did is I just keep everything same, but what I do is I do a nonlinear contact. I set nonlinear contact for this particular contacts between this and this, and then let me run this one. So please note that we are running a nonlinear simulation, and still the speed is quite amazing. Now if I go to the displacement again, so this is my design study one, structural one, in the sense this one which is linear. If I go over here, so this is my structural 2. I don't know whether you could observe this or not. So you have to observe this area. Okay, let me take a pen, if I can take a pen. I don't know whether how to take a pen. Yeah, there is a pen. Okay, so if you have to observe this area. Okay, so if I go over here, um, this is my design study structural 2. You see the gap over here, and this is my structural one. See the gap over here. So that's what is happening with the nonlinear behavior. So with nonlinear behavior, this is much more, it is separating out, and with linear bonded, these things are actually stick together. So that's how it is in line with the physics itself, right? So let me find out if I can erase this erase these things, erase all right. Okay, so now if I go to the second one, so that is my stress. So this is my linear in the bonded contact, and you will see that most of the load are getting passed from this area. Now if I go over here, suddenly what happens is the loads are not getting passed from the beam 1 to beam 2. Rather, this bolts started taking load. If you see this over here, let me play again. So this is my linear one where loads are getting passed from the beam because those are bonded. And after I make it non-linear, you see that bolts are started getting load. Okay, so now let's do one more iterations. Okay, let's do one more iteration. So what I'll do this time is I'll copy this nonlinear study, copy this one, make it linear study, nonlinear study 2, structure nonlinear 2, and let me bring all those parts. And what I'll do is I'll apply some torque here. Okay, I'll apply some torque here. So let me take this bolt, 4 bolt. Okay, and then make it 1.25, sorry, 1.25 mm as my pitch, and let me apply a torque of 1 turn. Okay, so let me apply this torque. Okay, so now if I run this again, so let me run this simulation again, structural 3. Okay, so it's now running with nonlinear analysis, nonlinear contact analysis with pretension of bolt. Okay, so now if I go again to this displacement, so this is my displacement, that is structural 1, in the sense the first load case. This is for structural 2, that is we have already discussed. This is nonlinear load case without pretension, and this is my third load case with pretension. Let's go to the stress. So this is my stress. This is my stress. First load case, linear analysis. Second load case, bolts taking load. Third load case. So now this is where magic happens. So if you see this one, this is also non-linear. This is also non-linear. Bolts are taking load, and this is non-linear. This is non-linear. But now this time what happens is that all the bolts, because we have given a pretension, all the bolts are uniformly taking load, which was not the case over here. Only these two bolts are taking load, these bolts are not taking load. This is where the nicely all the bolts are taking load. So that's the power of SimSolid. I mean, we are doing complex physics simulation, but without getting into complexity of doing the things. All we are doing is we are just making decision out of those complex behavior, and that can be done very easily within SimSolid. So with that, I am stopping this demo as well. I'm moving to my next demonstration, which is FRF. Okay, frequency response analysis. Okay, so for that, let me go over here. Let me close this. Let me bring that model. I think we can go over here itself. So FRF, and let me bring this model. Okay. Okay, so this is a big assembly. This is a real big assembly in the sense that this is a complete structure. Earlier we did analysis of only this portion. Now we have this complete assembly of this whole structure with these frames and all those things. And we are going to do what is called a frequency response analysis. Okay, so there is already one study is done. So what I'll do is I'll not I'll just copy this one. So I'll make a new design study, and I'll probably delete all those things. So what they have done is actually they have done just the modal analysis. Okay, I think that will make sense. That will okay. So let me delete this. So what they have done is they have done a modal analysis, and they actually set up the mode analysis for 10 modes, which you already know how to set up. And how the setup is this. So this is like this. So what they have done is they have fixed this area. So fix this base. And also what they have done is they have applied a constraint in the sense that these things should not move in the y direction. So that's the constraint they have applied. If you see it over here, so this constraint is talking about that. So it is telling that we should not, this part should not move in y direction. That is obvious to make a capture the real physics, because when you lift a log and all, it normally don't go in this direction. So that's what has been replicated over here. Okay, so that's how it is. So that is the setup. So in short, this is fixed over here, and this is not allowed to move in this direction. Rest of the connections and all are defined like we have done so far. Material has been defined. Now I'll run the mode analysis. Let me run this mode analysis. So it is going to extract 10 modes for a assembly, which is quite big. I think it will have more than, say, my guess is around, say, 150 components. Let's see. I'll have a measurement after this assembly simulation is done. But it is quite a big assembly to my opinion, and it will take reasonably a large amount of time if you want to solve it in conventional way. Excuse me, let me have some water. Assembly and get the statistics. So it has around oh, there is 500 components. Okay, so this has 500 components, and if you see the size, it is say 5 meter. So 500 components, 5 meter, 38-second modal analysis for 10 modes. That is amazing. Okay, but that's not what we are interested now. So let's see what are the modes, at least before we go forward. So if you see this first mode, so quite obvious, first mode will come like this. Okay, so these are first mode. Second mode is coming like this. Okay, and third mode is the twisting mode. Okay, so the first mode is in, say, X direction, second mode is in Z direction, and then afterwards there are complicated modes. Okay, so that's what it is. So now what we'll do is we'll do a frequency response analysis. Okay, how to do that? And why to do that? So that's the two question. Why part I'll leave it to you. You are engineers, you know why to do that. So let me show how to do that. Okay, so I'll go over here, frequency response analysis. You have to take that type of analysis over here, and then as soon as it will come, so it will link a model. So there is a model link. If you have multiple design study, then you may have to manually link, but since we have only design study, so we have sorry, the only one part. So we have linked this model, and it will also link set the upper and lower limit of the frequency based on your modal analysis. Okay, and then you have option of applying damping ratio. That can be each frequency based, or you can set a global as well. So here we have to set a global one and say okay. So my setup is ready now. Second thing what you have to do is you have to create a what is called frequency function. Okay, so now the frequency function can be a imported CSV, or it can be a standard say maybe harmonics. So maybe harmonics function with amplitude say 10 and say frequency of say 5. Okay, and say okay, so this is my frequency function. You can even import your own function as well, CSV file, and say this is my frequency function. And then what you will do is if I go over here, okay, so this is one is done, and then okay, frequency function is done, setup is done. Now next what we will do is I will apply something what is called base excitation. Okay, so now when you apply base excitation or any type of load, it's not necessary that you only have to apply base excitation, but for this kind of geometry, we maybe base excitation would be most efficient. So you can apply it in any form. So right now what I will apply is I will apply a 10g acceleration in Z direction. Okay, so in Z direction, so that means I have to make these two things 0, and it will follow this frequency function what we have applied. So that's simple. That's as simple as you can simply you can define it in SimSolid. Okay, so you say okay, so your frequency excitation is done. Now what we'll do is we'll go for analyzing this frequency response analysis. Okay, so I have shown just the frequency, or I am showing rather just the frequency response analysis, but you can also do random response analysis or transient analysis. And again, it's not at all complicated, as you have already come to conclusion, and the time taken is amazingly less. So you go over here. Now the surprise is happened is that now what we can check is that how it is going to behave. Okay, so what it is showing is that if I play this thing, and it will exactly show that how it is going to behave. And then if I stop it and show at peak in the sense that the first peak is coming, which location you show at that frequency. So it is coming 5.24 hertz. Okay, so if you remember, it's difficult to remember because I have just shown for a very momentarily. Let me show you again. So if I go to my modal analysis and check the result, check my result. So if you see that my first mode is actually 1.73. My first mode is 1.73, and my second mode is actually 5.2 or something. So normally what our assumption is that whatever the first mode is the most critical one. Okay, but FRF or maybe all these dynamic analysis are actually to help you to understand whether that is really a critical one based on your load application, which we can see it over here. So in this particular case, if you see it over here, your first mode is no more a critical one, your second mode become a critical one. Why? The reason is simple. We have applied a load in Z direction. Okay, so that's why we are getting a frequency which is not the first mode. The peak is not the first mode but the second mode. You can also understand many more things. For example, if I check this, it will show you that how those peaks are. Okay, basically the frequency values of those peaks. So in short, again, it is quantifying the same things. Okay, so those things you can understand from your dynamic analysis. With that, I'm ending the dynamic analysis demo again, and then moving to the next one, which is, I don't know which one. Let me check. What is my, okay, so what I want to show, okay, so I want to show the thermal one. So this is the last one, and then I'll go back to my last few slides of the presentation. Let me make some air circulation. Okay, so go back to the SimSolid. Let me open it. I think I can open from here as well. So let me open. So this is for thermal analysis. Okay, this to show thermal analysis. Now this particular case is a turbine turbocharger, rather not yeah, you can call it turbine. So there is a turbocharger of a engine. So what it does is, I don't like this color. So what it how the boundary condition over here is that this end is the hot end, and no, sorry, this is not the hot end. So this end is the hot end, this is the hot end, and this is the cold end, in the sense that this is connected with your engine and this is going ahead with the rest of the system. Okay, so what we have to define is that any surface inside this is around very high temperature, and then that is the source of heat, and then from this surface it will emit the heats in convection, and then there are other areas as well for the heat convection, heat loss is concerned. So to very simple to do it in SimSolid, all you have to do is you have to go over here, thermal analysis, check thermal analysis, and then you have to define your temperature. So this particular face, all the faces I have to define, so that's why I have to switch this on, and then I'll choose the temperature what I need over here. So maybe I'll make a 1200 degree centigrade. I think this is little higher, but it's okay. Then what I'll do is I'll go for defining my again I have to make sure that this is checked. So define this area where ambient is say 30 degrees centigrade, and convection heat also maybe around 1000 you can say. So there is one area, and then I will also let me hide this one. Let me hide this. Let me hide this. Let me let me hide this. So I would also like to apply some convective thermal convection over here. So maybe I'll apply one by one, so that so here temperature will be little higher. So maybe say 200 degrees centigrade, and again let's assume that the same convective heat transfer coefficient is there. So this is one. Then I can also apply another convective heat transfer coefficient over here. So let me apply over, oops. Okay, so you have to make sure that I am not applying the same condition again. So let me, okay, so let me be careful while selecting those parts. So let me apply this over here. And again, I have to make 200 ambient, and then 1000 over here, and then I will apply another convective coefficient. I could have applied actually together as well, but I'm just making sure I don't miss any surface. So that's why I'm taking extra care. Okay, so now my definition is complete. Boundary condition definition is complete. I also have to make connections, otherwise it will not work. So what it will do is it will create connections which will be which will be converted into that thermal contacts. Okay, so once I have that, I can go for running this analysis. Again, I have not assigned material. I want to use the default material, so I'm saying yes. Okay, so it's going to its solving is done. Now I can go and check my results over here. Oops, not thermal. I want to make temperature. So you'll see that as I this is my heat source and how the temperature is cooling down. If you want a gradient, that is also possible. So you can take a line over here and then probably plot that with respect to length how the temperature gradient is, or you can even understand the different locations, or you can understand the flux and other types of entities as well. So with that, I kind of came to the end of this demonstration part. I'll go quickly to my presentation again, and I'll skip this. I'll go directly over here. Okay, so we have discussed almost all of these things. So as far this slide's talking about the summary of the features available within SimSolid. So it has the solutions. As far as the solution goes, it has modal, linear static, non-linear static, frequency response, transient response, random response, thermal stress, inertia relief, bolt precision. Many of this we have covered today. Some of them we have not covered, but those capabilities are also available. It covers isotropic, elastoplastic, rigid as well as user extensible. So these are important because you can sometimes need rigid materials and all as far as the material is concerned. You can create different types of connection, which includes auto connection, bonded connections, bolted connections, welded connections, virtual connections, and you can see almost all types of result which you may be required for any engineering analysis. Now bolt tightening loads we are capable of doing. We already seen this. You can create spot oils, fillet oils for as big as this whole chassis. You can create contacts. We have seen this, but again, there's another example where sliding contacts may be of useful, or maybe separating contacts. So for example, a nonlinear separating contacts where the separation happens because of the external forces. Geometric nonlinearity we have not covered today, but this is capable of doing. You can even combine geometric and material nonlinearity together, so that is also possible. And here you can understand that how the elastic load, elastic behavior, plastic behavior, as well as after you load withdrawal, what is the behavior. So all those things you can understand. Transient dynamic also you have not covered, but you can do that in dynamic, similar like what we did in FRF. Okay, so what our customer says, so the Renault Nissan was recently, they are using extensively, and they recently published a presentation, video presentation, where they published their findings. And what it is saying is that accuracy is around say 5 to 10%. It's not accuracy, it's error, in the sense that accuracy is around say 90 to 95%. And they tried it for multiple types of projects, subframe, then your bars, then chassis components, and many components they have tried, and they found good results, and they are happy to publish the video testimonial, as well as not video testimonial, presentation. Dunbar is one of our customer who are into trailer, UK based, and they have a video testimonial. Again, it's available within YouTube if you are interested. Search Dunbar SimSolid testimonial, you will understand what he is talking. They use SimSolid SolidWorks as their CAD platform, and they also have SolidWorks simulation available, but they moved out of SolidWorks simulation to SimSolid because of the speed and accuracy and the power it provides. Serapit is a very old customer who I think this is the first case study we got. There are many customers, but we don't have many case studies what are published. But Serapit was the bold one who allowed us to publish the case study. And if you see their structure, it's quite complicated in terms of number of parts, number of assemblies, number of chain, number of joints, and they need no other tool than SimSolid probably serve their purpose. Andron Handling is a SPM company which makes this is the tire handling equipment machine, and if you see that again it has complexities in terms of joint connections and the geometries. So here they can use SimSolid without simplifying, in the sense that they don't have to remove those tire and put a point mass and all those kind of jugglery they don't have to do. They just do this complete assembly, what is going to be with their customers they can take and then do the analysis. Lamprell is another customer who makes the very big, very large assemblies of offshore structures, and they obviously they found benefit of SimSolid. Brompton, there is a bike company. They use SolidWorks, and then they get use SimSolid for purposes. So other examples such as general machinery, some of them time and number of components comparison has been given. So for example, this particular parts has I don't know, 23 part assembly 0.5 minutes, 344 parts 0.5 minutes, 3000 parts 2 minutes, and so on and so forth. Okay, so these are very large components. These are 7700 components and takes 30 minutes. So these are many examples out there, and there are many examples in public domain as well available. You can search. Now this talks about the speed, accuracy, and power. Speed, power, and capabilities of SimSolid, what we have discussed so far. So now there might be obvious question with you, how accurate it is. Okay, so there are many ways you can answer this question. The first one is that we have published a what is called verification manual, which kind of verify all the 88 NFM's cases, and which are kind of industry standard. And you can go through that paper, verification manual, and you can yourself be surprised with the accuracy of SimSolid. We also have many external customer verification, which they compared it with our competitor, which you cannot show because obvious reason. This one we have compared with our own solver, which is OptiStruct, and this is a component which is it's a golf driver head. So this particular components is peculiar in nature, because what happens is for a avid golfer, he has to understand the noise coming out after he hit this ball with this golf head, and based on the noise he judge whether his shot is good or bad. Now to do that, you have to understand that we have to maintain a particular natural frequency of this component to emit those kind of noise. So in short, the natural frequencies of this or modal analysis is a very critical performance measurement criteria for this kind of components, and we did it that modal analysis in SimSolid as well as OptiStruct. And if you see the result difference, it's not more than 1%, whereas the time is a huge benefit what we got as far as the SimSolid is concerned vis-a-vis the conventional methods. There are individual freelance experts. For example, Rich King, he's a very popular face is as far as the simulation codes development are concerned, and he wrote his own paper comparing ourselves with many of those other similar softwares, and you can yourself get those papers online. This is a testimonial from one of our customer who is our first customer. There is a Tata DLT. If you see it over here, they make again they make a trailer, and they are quite extensively using for different load cases, and they are very happy with the product. These are some of the customer name in India. I am sure I missed many because this slide is not updated recently, but this will give you a glimpse of the range and breadth of the customer who are using SimSolid in their production. With that, I came to the end, and I would open the floor for answering the questions. So let's see what are the questions we have.